Welcome back. I got a shower and a shaving. I did really need it. It's 4 p.m. I start to get tired because it's so hot. So hot always in my apartment. It was 27, but now the temperature dropped a little bit. But it's like a greenhouse and it makes me very sleepy because it's so hot and like a jungle, not greenhouse. I like to read this, but I not understand what it is properly, but I like to read it anyway. So I got a shower and a shaving, and I need to cook hot food later.
Nanomaterials. Nanomaterials describe, in principle, chemical substances or materials of which a single unit is sized, in at least one dimension, between 1 and 100 nm, the usual definition of nanoscale. Nanomaterials research takes a materials science-based approach to nanotechnology, leveraging advances in materials metrology and synthesis which have been developed in support of microfabrication research. Materials with structure at the nanoscale often have unique optical, electronic, thermophysical or mechanical properties. Nanomaterials are slowly becoming commercialized and beginning to emerge as commodities. Definition, edit. In ISO /TS 80004, nanomaterial is defined as the material with any external dimension in the nanoscale or having internal structure or surface structure in the nanoscale, with nanoscale defined as the length range approximately from 1 nm to 100 nm. This includes both nano-objects, which are discrete pieces of material, and nanostructured materials, which have internal or surface structure on the nanoscale. A nanomaterial may be a member of both these categories. On the 18th of October, 2011, the European Commission adopted the following definition of a nanomaterial. A natural, incidental or manufactured material containing particles, in an unbound state or as an aggregate or as an agglomerate and for 50% or more of the particles in the number-size distribution, one or more external dimensions is in the size range 1 nm 100 nm. In specific cases and where warranted by concerns for the environment, health, safety or competitiveness, the number-size distribution threshold of 50% may be replaced by a threshold between 1% to 50%. Sources, edit. Engineered, edit. Engineered nanomaterials have been deliberately engineered and manufactured by humans to have certain required properties. Legacy nanomaterials are those that were in commercial production prior to the development of nanotechnology as incremental advancements over other colloidal or particulate materials. They include carbon black and titanium dioxide nanoparticles. Incidental, edit. Nanomaterials may be unintentionally produced as a byproduct of mechanical or industrial processes through combustion and vaporization. Sources of incidental nanoparticles include vehicle engine exhausts, smelting, welding fumes, combustion processes from domestic solid fuel heating and cooking. For instance, the class of nanomaterials called fullerenes are generated by burning gas, biomass, and candle. It can also be a byproduct of wear and corrosion products. Incidental atmospheric nanoparticles are often referred to as ultrafine particles, which are unintentionally produced during an intentional operation, and could contribute to air pollution. Natural, edit. Biological systems often feature natural, functional nanomaterials. The structure of foraminifera, mainly chalk, and viruses, protein, capsid, the wax crystals covering a lotus or nasturtium leaf, spider and spider mite silk, the blue hue of tarantulas, the spatulae on the bottom of gecko feet, some butterfly wing scales, natural colloids, milk, blood, horny materials, skin, claws, beaks, feathers, horns, hair, paper, cotton, nacre, corals, and even our own bone matrix are all natural organic nanomaterials. Natural inorganic nanomaterials occur through crystal growth in the diverse chemical conditions of the Earth's crust. For example, clays display complex nanostructures due to anisotropy of their underlying crystal structure, and volcanic activity can give rise to opals, which are an instance of unnaturally occurring photonic crystals due to their nanoscale structure. Fires represent particularly complex reactions and can produce pigments, cement, fumed silica, etc. Natural sources of nanoparticles include combustion products, forest fires, volcanic ash, ocean spray, and the radioactive decay of radon gas. Natural nanomaterials can also be formed through weathering processes of metal or anion-containing rocks, as well as at acid mine drainage sites. Gallery of natural nanomaterials. 1. Viral capsid. 2. Lotus effect, hydrophobic effect with self-cleaning ability. 3. Close-up of the underside of a gecko's foot as it walks on a glass wall, spatula, 210-15 nm. 4. SEM micrograph of a butterfly wing scale, 5000. 5. Peacock feather, detail. 6. Brazilian crystal opal. The play of color is caused by the interference and diffraction of light between silica spheres, 150-300 nm in diameter. 7. Blue hue of a species of tarantula, 450 nm plus or minus 20 nm. Types, edit. Nanomaterials are often categorized as to how many of their dimensions fall in the nanoscale. A nanoparticle is defined a nano-object with all three external dimensions in the nanoscale, whose longest and the shortest axes do not differ significantly. A nanofiber has two external dimensions in the nanoscale, with nanotubes being hollow nanofibers and nanorods being solid nanofibers. A nanoplate /nanosheet has one external dimension in the nanoscale, and if the two larger dimensions are significantly different it is called a nanoribbon. For nanofibers and nanoplates, the other dimensions may or may not be in the nanoscale, but must be significantly larger. In all of these cases, a significant difference is noted to typically be at least a factor of 3. Nanostructured materials are often categorized by what phases of matter they contain. A nanocomposite is a solid containing at least one physically or chemically distinct region or collection of regions, having at least one dimension in the nanoscale. A nanofoam has a liquid or solid matrix, filled with a gaseous phase, where one of the two phases has dimensions on the nanoscale. A nanoporous material is a solid material containing nanopores, voids in the form of open or closed pores of submicron length scales. A nanocrystalline material has a significant fraction of crystal grains in the nanoscale. Nanoporous materials, edit. Main article, Nanoporous materials. The term nanoporous materials contains subsets of microporous and mesoporous materials. Microporous materials are porous materials with a mean pore size smaller than 2 nm, while mesoporous materials are those with pore sizes in the region 250 nm. Microporous materials exhibit pore sizes with comparable length scale to small molecules. For this reason such materials may serve valuable applications including separation membranes. Mesoporous materials are interesting towards applications that require high specific surface areas, while enabling penetration for molecules that may be too large to enter the pores of a microporous material. In some sources, nanoporous materials and nanofoam are sometimes considered nanostructures but not nanomaterials because only the voids and not the materials themselves are nanoscale. Although the ISO definition only considers round nanoobjects to be nanoparticles, other sources use the term nanoparticle for all shapes. Nanoparticles, edit. Main article, nanoparticle. Nanoparticles have all three dimensions on the nanoscale. Nanoparticles can also be embedded in a bulk solid to form a nanocomposite. Fullerenes, edit. Main article, fullerene. The fullerenes are a class of allotropes of carbon which conceptually are graphene sheets rolled into tubes or spheres. These include the carbon nanotubes, or silicon nanotubes, which are of interest both because of their mechanical strength and also because of their electrical properties. The first fullerene molecule to be discovered, and the family's namesake, Buckminster fullerene, C60, was prepared in 1985 by Richard Smalley, Robert Curl, James Heath, Sean O'Brien, and Harold Crotto at Rice University. The name was a homage to Buckminster Fuller, whose geodesic domes it resembles. Fullerenes have since been found to occur in nature. More recently, fullerenes have been detected in outer space. For the past decade, the chemical and physical properties of fullerenes have been a hot topic in the field of research and development, and are likely to continue to be for a long time. In April 2003, fullerenes were under study for potential medicinal use, binding specific antibiotics to the structure of resistant bacteria and even target certain types of cancer cells such as melanoma. The October 2005 issue of Chemistry and Biology contains an article describing the use of fullerenes as light-activated antimicrobial agents. In the field of nanotechnology, heat resistance and superconductivity are among the properties attracting intense research. A common method used to produce fullerenes is to send a large current between two nearby graphite electrodes in an inert atmosphere. The resulting carbon plasma arc between the electrodes cools into sooty residue from which many fullerenes can be isolated. There are many calculations that have been done using ab initio quantum methods applied to fullerenes. By DFT and TDDFT methods one can obtain IR, Raman, and UV spectra. Results of such calculations can be compared with experimental results. Metal-based nanoparticles, edit. Inorganic nanomaterials, for example quantum dots, nanowires, and nanorods, because of their interesting optical and electrical properties, could be used in optoelectronics. Furthermore, the optical and electronic properties of nanomaterials which depend on their size and shape can be tuned via synthetic techniques. There are the possibilities to use those materials in organic material-based optoelectronic devices such as organic solar cells, OLEDs, etc. The operating principles of such devices are governed by photon-induced processes like electron transfer and energy transfer. The performance of the devices depends on the efficiency of the photon-induced process responsible for their functioning. Therefore, better understanding of those photon-induced processes in organic/inorganic nanomaterial composite systems is necessary in order to use them in optoelectronic devices. Nanoparticles or nanocrystals made of metals, semiconductors, or oxides are of particular interest for their mechanical, electrical, magnetic, optical, chemical and other properties. Nanoparticles have been used as quantum dots and as chemical catalysts such as nanomaterial-based catalysts. Recently, a range of nanoparticles are extensively investigated for biomedical applications including tissue engineering, drug delivery, biosensor. Nanoparticles are of great scientific interest as they are effectively a bridge between bulk materials and atomic or molecular structures. A bulk material should have constant physical properties regardless of its size, but at the nanoscale this is often not the case. Size-dependent properties are observed such as quantum confinement in semiconductor particles, surface plasmon resonance in some metal particles, and superparamagnetism in magnetic materials. Nanoparticles exhibit a number of special properties relative to bulk material. For example, the bending of bulk copper, wire, ribbon, etc., occurs with movement of copper atoms forward/clusters at about the 50 nm scale. Copper nanoparticles smaller than 50 nm are considered super-hard materials that do not exhibit the same malleability and ductility as bulk copper. The change in properties is not always desirable. Ferroelectric materials smaller than 10 nm can switch their polarization direction using room temperature thermal energy, thus making them useless for memory storage. Suspensions of nanoparticles are possible because the interaction of the particle surface with the solvent is strong enough to overcome differences in density, which usually result in a material either sinking or floating in a liquid. Nanoparticles often have unexpected visual properties because they are small enough to confine their electrons and produce quantum effects. For example, gold nanoparticles appear deep red to black in solution. The often very high surface area to volume ratio of nanoparticles provides a tremendous driving force for diffusion, especially at elevated temperatures. Sintering is possible at lower temperatures and over shorter durations than for larger particles. This theoretically does not affect the density of the final product, though flow difficulties and the tendency of nanoparticles to agglomerate do complicate matters. The surface effects of nanoparticles also reduces the incipient melting temperature. One-dimensional nanostructures, edit. The smallest possible crystalline wires with cross-section as small as a single atom can be engineered in cylindrical confinement. Carbon nanotubes, a natural semi-1D nanostructure, can be used as a template for synthesis. Confinement provides mechanical stabilization and prevents linear atomic chains from disintegration. Other structures of 1D nanowires are predicted to be mechanically stable even upon isolation from the templates. Two-dimensional nanostructures, edit. 2D materials are crystalline materials consisting of a two-dimensional single layer of atoms. The most important representative graphene was discovered in 2004. Thin films with nanoscale thicknesses are considered nanostructures, but are sometimes not considered nanomaterials because they do not exist separately from the substrate. Bulk nanostructured materials, edit. Some bulk materials contain features on the nanoscale, including nanocomposites, nanocrystalline materials, nanostructured films, and nanotextured surfaces. Box-shaped graphene, BSG, nanostructure is an example of 3D nanomaterial. BSG nanostructure has appeared after mechanical cleavage of pyrolytic graphite. This nanostructure is a multilayer system of parallel hollow nanocornels located along the surface and having quadrangular cross-section. The thickness of the channel walls is approximately equal to 1 nm. The typical width of channel facets makes about 25 nm. Applications, edit. Main article, Applications of Nanotechnology. Nanomaterials are used in a variety of manufacturing processes, products and healthcare including paints, filters, insulation and lubricant additives. In healthcare, nanozymes are nanomaterials with enzyme-like characteristics. They are an emerging type of artificial enzyme, which have been used for wide applications in such as biosensing, bioimaging, tumor diagnosis, antibiofueling and more. High-quality filters may be produced using nanostructures. These filters are capable of removing particulate as small as a virus, as seen in a water filter created by Selden Technologies. Nanomaterials membrane bioreactor, NMS-MBR, the next generation of conventional MBR, are recently proposed for the advanced treatment of wastewater. In the air purification field, nanotechnology was used to combat the spread of MERS in Saudi Arabian hospitals in 2012. Nanomaterials are being used in modern and human-safe insulation technologies. In the past they were found in asbestos-based insulation. As a lubricant additive, nanomaterials have the ability to reduce friction in moving parts. Worn and corroded parts can also be repaired with self-assembling anisotropic nanoparticles called TurboTEX. Nanomaterials have also been applied in a range of industries and consumer products. Mineral nanoparticles such as titanium oxide have been used to improve UV protection in sunscreen. In the sports industry, nitobats have been produced with carbon nanotubes to improve performance. Another application is in the military, where mobile pigment nanoparticles have been used to create more effective camouflage. Nanomaterials can also be used in three-way catalyst, TWC, applications. TWC converters have the advantage of controlling the emission of nitrogen oxides, NOx, which are precursors to acid rain and smog. In core shell structure, nanomaterials form shell as the catalyst support to protect the noble metals such as palladium and rhodium. The primary function is that the supports can be used for carrying catalysts' active components, making them highly dispersed, reducing the use of noble metals, enhancing catalysts' activity, and potentially improving the stability. Synthesis, edit. The goal of any synthetic method for nanomaterials is to yield a material that exhibits properties that are a result of their characteristic length scale being in the nanometer range, 1/100 nm. Accordingly, the synthetic method should exhibit control of size in this range so that one property or another can be attained. Often the methods are divided into two main types, bottom-up and top-down. Bottom-up methods, edit. Bottom-up methods involve the assembly of atoms or molecules into nanostructured arrays. In these methods the raw material sources can be in the form of gases, liquids, or solids. The latter require some sort of disassembly prior to their incorporation onto a nanostructure. Bottom-up methods generally fall into two categories, chaotic and controlled. Chaotic processes involve elevating the constituent atoms or molecules to a chaotic state and then suddenly changing the conditions so as to make that state unstable. Through the clever manipulation of any number of parameters, products form largely as a result of the ensuring kinetics. The collapse from the chaotic state can be difficult or impossible to control, and so ensemble statistics often govern the resulting size distribution and average size. Accordingly, nanoparticle formation is controlled through manipulation of the end state of the products. Examples of chaotic processes are laser ablation, exploding wire, arc, flame pyrolysis, combustion, and precipitation synthesis techniques. Controlled processes involve the controlled delivery of the constituent atoms or molecules to the site, S, of nanoparticle formation such that the nanoparticle can grow to a prescribed sizes in a controlled manner. Generally the state of the constituent atoms or molecules are never far from that needed for nanoparticle formation. Accordingly, nanoparticle formation is controlled through the control of the state of the reactants. Examples of controlled processes are self-limiting growth solution, self-limited chemical vapor deposition, shaped pulse photoscanned laser techniques, plant and microbial approaches, and molecular beam epitaxy. Top-down methods, edit. Top-down methods adopt some force, e.g. mechanical force, laser, to break bulk materials into nanoparticles. A popular method involves mechanical break-apart bulk materials into nanomaterials is ball milling. Besides that, nanoparticles can also be made by laser ablation, which apply short pulse lasers, e.g. femtosecond laser, to ablate a target, solid. Characterization, edit. Main articles, Nanometrology and characterization of nanoparticles. Novel effects can occur in materials when structures are formed with sizes comparable to any one of many possible length scales, such as the de Broglie wavelength of electrons, or the optical wavelengths of high-energy photons. In these cases, quantum mechanical effects can dominate material properties. One example is quantum confinement, where the electronic properties of solids are altered with great reductions in particle size. The optical properties of nanoparticles, for example fluorescence, also become a function of the particle diameter. This effect does not come into play by going from macroscopic to micrometer dimensions, but becomes pronounced when the nanometer scale is reached. In addition to optical and electronic properties, the novel mechanical properties of many nanomaterials is the subject of nanomechanics research. When added to a bulk material, nanoparticles can strongly influence the mechanical properties of the material, such as the stiffness or elasticity. For example, traditional polymers can be reinforced by nanoparticles, such as carbon nanotubes, resulting in novel materials which can be used as lightweight replacements for metals. Such composite materials may enable a weight reduction accompanied by an increase in stability and improved functionality. Finally, nanostructured materials with small particle size, such as zeolites and asbestos, are used as catalysts in a wide range of critical industrial chemical reactions. The further development of such catalysts can form the basis of more efficient, environmentally friendly chemical processes. The first observations and size measurements of nanoparticles were made during the first decade of the 20th century. Zsigmondy made detailed studies of gold sols and other nanomaterials with sizes down to 10 nm and less. He published a book in 1914. He used an ultramicroscope that employs a dark field method for seeing particles with sizes much less than light wavelength. There are traditional techniques developed during the 20th century in interface and colloid science for characterizing nanomaterials. These are widely used for first-generation passive nanomaterials specified in the next section. These methods include several different techniques for characterizing particle size distribution. This characterization is imperative because many materials that are expected to be nano-sized are actually aggregated in solutions. Some of methods are based on light scattering. Others apply ultrasound, such as ultrasound attenuation spectroscopy for testing concentrated nanodispersions and microemulsions. There is also a group of traditional techniques for characterizing surface charge or zeta potential of nanoparticles in solutions. This information is required for proper system stabilization, preventing its aggregation or flocculation. These methods include microelectrophoresis, electrophoretic light scattering, and electroacoustics. The last one, for instance colloid vibration current method, is suitable for characterizing concentrated systems. Mechanical properties, edit. The ongoing research has shown that mechanical properties can vary significantly in nanomaterials compared to bulk material. Nanomaterials have substantial mechanical properties due to the volume, surface, and quantum effects of nanoparticles. This is observed when the nanoparticles are added to common bulk material, The nanomaterial refines the grain and forms intergranular and intragranular structures which improve the grain boundaries and therefore the mechanical properties of the materials. Grain boundary refinements provide strengthening by increasing the stress required to cause intergranular or transgranular fractures. A common example where this can be observed is the addition of nanosilica to cement, which improves the tensile strength, compressive strength, and bending strength by